Now we start with the second video on gravitation, gravitational field and its intensity. Now what do we mean by this term field? We take a mass m and a region of space around this mass. A region of space around this mass. Now this region means boundary line which is not fixed. Why not fixed? Because we have taken the boundary to be such a point, such a line where the f is equal to 0. Now what if we place any mass of unit mass or mass small m in this region, this mass will experience attraction force due to this mass. So if we place a mass m is equal to 1 unit here, that means this mass is going to feel an attraction force because of this larger mass in this direction. Now we can say that this force extends up to infinity from the relation a proportional to 1 by r square. This is the distance r. Now a proportional to 1 by r square means f can be 0 at r tends to infinity. That means this is the margin of infinity or infinity as you call it. Now infinity means there is no fixed line because infinity is undefined. So f is equal to 0 at r is equal to infinity. It is a theoretical statement. In practice, actually in practicality or in actual practice, the gravitational field may become too weak to be measured beyond a particular distance. Now what is gravitational field? We have discussed here. Field means this region of space around this mass in which a unit mass or test mass being placed, it will feel an attraction force due to this mass at a distance of r. So the field means the force that this mass feels is the field intensity at this point. The force that this unit mass feels is the field intensity, the value of field intensity at this point. Now what is the value of field intensity or gravitational field intensity? We can say the field intensity, you can take it to be I. So f by m, gravitational field intensity is a vector quantity, f is a vector quantity, m is a scalar quantity. By definition we can call it's the gravitational field intensity at a point, that means this point within a gravitational field. Within a gravitational field is defined as a gravitational force per unit mass placed at this point. Now per unit mass means this mass is the test mass and not the mass due to which this field has occurred. This is the test mass. We can take this mass to be 1 unit. As I have said, the field intensity is a vector quantity whose direction is same as that of the gravitational force. Now the SI unit of this field intensity is, this is in Newton, this is kg. So simply we can write Newton per kg. The dimensions of intensity is equal to force by mass, so m lt minus 2 by m, so it becomes lt minus 2. Now if we can look at this dimension lt minus 2, this is the dimension of acceleration. So somehow or the other this is related to an acceleration. Now how can we find that out? Let us take the force of attraction G is equal to G m by r square from these two masses. We can understand that there is an attraction force between these two masses mm. So G mm by r square. Now what is this force? If we take the earth, we place a mass at the surface, small m. The force with which the earth attracts the body, we know that it to be the weight of the body. So this force becomes mg, and According to Newton's law of gravitation, the attraction force between the earth of mass capital M and this body of mass small m is this one. So gmm by, we can replace this r as r square or the radius of the earth. So m gets cancelled out as m not equal to 0. So g is equal to gm by r square. Now the value of this gm by r square can also be related to this statement as f by m. If we take m onto the left hand side, the right hand side becomes gm by r square. So f by m means g, this is g. So f by m, from this relation we have found out to be I, or the intensity. Now intensity becomes this g. So the acceleration due to gravity is indirectly called the intensity of the gravitational field. That is why we were getting the dimension of this intensity as Lt minus 2. That is the dimension of an acceleration. So acceleration means the acceleration due to gravity. So it is equal to the intensity of the field, gravitational intensity of gravitational field. Intensity of gravitational field. Now, gravitational field intensity due to spherical mass distribution. This is a very important topic related to joint entrance. Now, if the observation point is located on the surface or outside the surface, then the spherical mass can be taken as a particle which is situated at the center of the sphere. Two cases, that means the sphere, if this is the sphere, now observation point is on the surface or outside the surface. If these are the two cases, we can take into account the spherical mass to be a point mass concentrated at the center. We can take this big mass to be concentrated at this center for these two cases. But if the point is located inside the spherical mass, we cannot take that to be concentrated, or the mass of the spherical mass to be concentrated at the center of the sphere. That means we cannot take it to be a point mass. Now, number one, for solid sphere, we will take two cases. One is a solid sphere, and and the other is a spherical shell. Now, m is the mass of sphere. We can take r to be the radius of sphere, and small r to be the distance of the point under consideration from center of earth, always from the center of the earth. Now for case 1, we can take it to be r greater than r. That means the point is located outside the sphere. Outside the sphere. Now if the point is located outside the sphere, then we can take the intensity to be in the form of I out. That is gm by r square minus r cap. So the point is outside the sphere. Now suppose the point is outside the sphere, means this is a sphere, this is radius r, the point is outside the sphere. Distance between this point and this point is r. Suppose from O to P, this is r, and the radius of the sphere is capital R. Now, second case, case number 2. R equal to r, that means on the surface or at the surface. On the surface or at the surface, you can write, that means I surface equal to again gm by, now this r will be replaced by the radius of the sphere, that is r square, and the rest remains the same. That means this point is now here. This point is now on the surface of the sphere. So OP. Now case number 3. R less than R. That means the point is inside the sphere or solid sphere. That is inside. Inside the sphere. Now for solid sphere, I in will be gm by r square minus of r cap, the direction. Now this is similar to the value that you have got for the case of r greater than r. Same thing, r was outside the sphere, now r is inside the sphere. Now we know m dash by m is equal to v dash into rho by v into rho. That means 4/3 pi r cube into rho by 4/3 pi r cube into rho equal to r cube by r cube is equal to, or implies that m dash by m is equal to r cube by r cube. Now what was m dash? It was m r cube by r cube. Now replacing the value of this m dash here, this was m dash. Now why this was m dash, not m? The difference between these two is that this was the mass of the earth or the mass of the sphere as a whole. Now why this is m dash? Because when the point is inside the sphere, now the attraction part of the sphere is this one and not the full sphere. The attraction part is of this radius, and the mass is not capital M but a reduced mass which we have mentioned as m dash. So m dash was m r cube by r cube. Now replacing the value of m dash in the last equation, we can get I is equal to I in, or rather the third case, I in was equal to gm r cube r square r cube minus r. So it becomes I in equal to gm r by r cube, gm r by r cube into minus r unit vector. So this is the value, original equation or the formula for I in. This is a vector quantity. Now we can run through a few conclusions from the first case. We had found that I out was proportional to 1 by r square. Now from the second case, the third case, we can find out I in was proportional to r, proportional to small r. And from that, from the third law, from the fourth we can get that I max. Now where was the maximum value? That means at surface, that was gm by r square. So the maximum value of intensity will be at the surface. Very important point to remember. And last but not the least, that is I center. That means what will be the value of intensity at the center of the sphere. That means gm by r cube into 0. In this formula we have replaced small r to be 0 because we have taken it to be the center of the sphere. Now you can take this as the I minimum. So this is the value of the maximum intensity, that is at the surface, and the minimum intensity value to be 0 at the center of the sphere. Now this is a very important graph, very important graph, I versus R. So this is the center of the sphere, solid sphere, sorry, graph of I versus R for a solid sphere. This is the surface of the sphere, out of the sphere, inside the sphere. I in proportional to R, that means it's a straight line directly proportional, and inversely proportional to the square of the distance. That means it is a inverse graph like this. Now why have we taken this to be in the fourth quadrant? That means of negative I, because every time we have tried to find out the value of I, we have got a minus R cap multiplied with the value of I, with the magnitude of I. So we have drawn that part as minus gm by r square. The negative value will be along this direction. Now second part, gravitational field intensity due to a spherical shell. The first part we have studied about the gravitational field intensity due to a solid sphere. Now this is a spherical shell, hollow inside. Case 1, similar cases to be examined. R greater than R, that is outside the sphere, the point is outside the sphere. Now this is the point P, which is outside the sphere. So I out will be gm by r square into minus of r cap, minus because of the attractive nature of the force. Now case 2 is if r equal to r, that means on the surface, then I surface equal to gm by r square into r unit vector. That means the point is now where? The point is on the sphere. This is r. So the distance between this center and the point P is capital R, or the radius of the sphere. Again, case 3 is if r is less than r, that means inside the sphere, inside the spherical shell, then I is equal to 0. If it is inside the spherical shell, it will be I equal to 0. Now the graph, similar graph, we can draw it like this. I versus R again. Take this to be the central position. Similar graph, gm by r square. This will be sorry surface r is equal to r, center, this is I, this is r, so the value here will be minus gm by r square. Similarly, as I is equal to 0, so this part will remain blank, and the only part that you can get is this one, I out proportional to 1 by r square. So this part will be blank because inside the sphere, that means r less than r, r greater than r, and r less than r will be blank because I is equal to 0 here.